Today I'm going to discuss about mechanical properties of matter. Mechanical property, that means there is some force and motion as well. Here, mechanical properties of matter is also known as elasticity. Many students know this chapter as elasticity. So, what is mechanical properties of matter? What is elasticity? We will discuss it. And what are the effects after that? So, generally, we will start with the term stress. The term stress. We all know about the force. When we apply something on any object, if the object's shape, size, or position of motion changes or try to be changed, that is called force. If you apply something on any object, if the shape, size, or motion of an object is affected, then we can say we have applied a force that has the SI unit of Newton. Like this, I'm taking a rod made up of steel. I'm taking a rod made up of steel. It is hanged by any wall or something. If we apply any force this way, we apply a force this way. So, the rod will be stretched. If the initial position is L, now this length will be L prime. The length is straight. So we can say that we have applied a force which can deform the original shape or size. That's why this applied force is also known as deforming force. This is what? Deforming force. Now, whenever we will withdraw this force, the actual rod, the rod will gain its original shape or size afterwards. Why? This is because of the tendency of elasticity. So here, first of all, we will discuss about the term stress. What is stress? We have applied a force here, and that is actually stored as the potential energy of that stream. Due to that, whenever we withdraw the deforming force, that force, another force will be realized here. That is actually known as restoring force. And due to this restoring force, the object regains its original shape or size or original configuration. So here, the deforming force is equal to the applied force, and that is equal to the restoring force. Okay? And then this force acts between this cross section only. Between this cross section only. That is the area of cross section. Okay? So here, pressure is the applied force upon unit area. Here pressure is applied force upon unit area. But the stress is same thing, but in a different way. That is actually the deforming force acting per unit area. That is called actually stress. Deforming force acting per unit area is called stress. So I think it is familiar to you now. The pressure and the stress are same quantities. That's why it will also have the units and dimension of pressure, deforming force, divided by area. We will have SI unit of Newton per meter square, that is also given as the name of great scientist Thomas Pascal. And CGS unit will be 9 per centimeter square. So this is actually stress. I am saying again, with the deforming force acting by unit area, that is called stress. That is the SI unit of Newton per meter square, which will have this deforming force of the dimension. We will have the dimension of pressure as well, which ml minus 2 divided by m square. That is m minus 1 minus 2. So deforming force has the SI unit of Pascal and has the dimension of ml minus 1 e minus 1. Now another term is introduced here. As you know, that when I have applied a force on any object, it gets stretched. Now, what is stretching? It gains an extra or additional length. As I have said, original length is L, and now initial final length is L prime. So we can say there is a change in length, that is L prime minus L. There is a change in length, that is L prime minus L. If we divide this change in length divided by original length, that is called actually strain. Especially it has the name of longitudinal strain, but now it is strain. So the change in configuration divided by the original quantity or original configuration, that is called strain. So we have concluded two terms. One is strain and another is stress. Here you can easily say that L is a kind of length and L is also length. So it is a ratio of two same quantities. That's why strain doesn't have any unit. Any unit or dimension. So strain doesn't have any unit or dimension. Okay. Now, as their dimension is, here we will conclude one more term. That is, there is a scientist, Robert Hooke. Actually, he was a great scientist, Robert Hooke. Actually, he has proven all the theories, but due to lack of technological things, he could not have completed. And that were completed before 150 years approximately. He was completed by Thomas Young. So here, there is a law that was given by Sir Robert Hooke, but it is completed by Thomas Young, and that is Pascal's law. What is Pascal's law? Pascal's law is actually in elastic limit. The stress and strain is directly proportional. In elastic limit, strain is directly proportional to stress. Strain is directly proportional to stress. So here a new term comes up. We can write strain equal to K into stress. Here K is the constant of proportionality. And we can say actually stress equal to K into strain. It will be easier for calculation. Here you can write K equals to stress by strain. Here K is the modulus of of proportionality, that in elasticity chapter or in mechanical properties of matter, you will say here, this is the modulus of elasticity. This is the modulus of elasticity. So in a clear way, you can say whenever stress happens, whenever we are applying any stress on any object, it results in a strain. There are different types of strains are there. I'm not going to talk about that today. And you will see here this modulus of elasticity. This one is modulus of elasticity. This modulus of elasticity has a unit of stress, as strain is unitless. It has a dimension of stress that as it has is strength dimensionless, strength is dimensionless. So we can say modulus of elasticity and stress both have the same unit